Okay, so just before we go into the next section here, see, it's not working again. What happened? Okay, I can't see my pointer. Why do you like that? Okay, good enough. I'm happy with that. Okay, so Ohm's law is written V equals IR, or if you want, R equals V over I. And the way to kind of think about that is to just imagine that you have a graph that looks like this. On this axis you have voltage, on this axis you have current, and what you'll find is, if this is sort of trying to represent like a circuit, right? Like here, and so you've got some resistor in this circuit. Let's say you can vary the voltage here, right? You can change it. You can raise and lower the voltage. Okay? What you'll find is you'll get a relationship, something like this. Okay, or maybe like this, or maybe like that. Yeah. This is just an ohmic resistor, correct. There are other kinds of resistors. So these are for resistors that follow Ohm's law. So if you look, if I were to take the rise over the run for this, okay, I'm getting delta V over delta I, okay, and what that's giving me is the slope here, okay, so the slope is never changing, the resistance is always the same, no matter what voltage or current I apply. You can think of the voltage as the push, and the current is how much gets through given that push, okay? So this is for what's called an ohmic resistor. These are ideal resistors. In real life, resistance is often affected by things like temperature. If you're dealing with semiconductors, and it gets all crazy. But in general, most resistors that we'll ever really deal with in terms of physics problems are going to be considered to be ohmic resistors. Okay, does that make sense? Light bulbs are not ohmic resistors. So, when we're trying to do some work on there, you always run into problems using that as a demonstration board because you're plugging light bulbs into it, and depending how much, depending whether there's other light bulbs in series, basically it depends on how hot they are, their resistance changes. So yeah. Things tend to, and correct me if I'm wrong, get more resistive as they get hotter. I believe that's correct. Okay. Okay. So that's just a quick review of Ohm's law. And we use that very extensively when we're trying to solve or figure out or analyze circuits. Okay. So next, let's talk about power. We haven't talked about power yet. Remind me, what is power from when we looked at our energy unit? What units is it measured in? Joules per second. And so basically what we're saying is power is going to be equal to energy over time. Okay? Joules, time in seconds. And what is the unit that we use to describe? Like, what's the joule per second called? Good. So 1 watt equals 1 joule per second. Okay, perfect. Now, where does this come into play in electricity? Well, it turns out that P, the power, is equal to the current multiplied by the voltage. Now, why is that true? What unit is current measured in? Coulombs per second. And voltage is measured in joules per coulomb. So if we take a look and we multiply through, coulombs times coulombs to the -1 canceled out, and we're left in joules per second. So there you go. P equals IV gives you a value in terms of watts. Okay? Power in watts is simply equal to I times B. Okay, now can we come up with some other interesting applications or ways of writing out this formula? So what happens if we want to out of time. What we'll do next time is we'll combine power with Ohm's law.